Howdy, howdy. I'm going to talk so that Zoom recording kind of catch up to everything. Often when I do a Zoom recording, it's very fuzzy at the beginning. So this this recording is to um, take the place of part of our reactions to class, which covers demonstrations of pretty much all the reactions we talk about, or most of we talk about. I'm doing the recording because often I find I don't have enough time in class to physically do it. I love to do it in class, but it just takes a lot of space. So we're just doing it here, the recording wise. And you know what? I'm doing this in 2024, and who knows? I might be using the recording in 2030 if I'm still teaching. So I hope you enjoy this a little bit as you kind of talk about the final reaction type, which is a double displacement reaction. So we just finished talking about the single displacement reaction, where you have some compound that's put together, and these compounds are going to combine with another compound. They're going to break apart, and one's going to combine with that new compound to form a new one. So it's kind of like you have two people dancing, and there's one person by itself, and then one person breaks off from the original dancing partner, another one person, and they kind of team up over here. So that's kind of like what the single displacement reaction is. Well, double is identical. It's just not single. It's double. So let me show you the back to the PowerPoint here real quick, if I can find it. Screen share. There we go. Okay, you should be seeing my screen here. So double displacement reaction. A double displacement reaction. Now, instead of having one compound break apart and one part of it will combine with another compound to form something brand new, you're going to have at least two compounds break apart. So the way we describe this when we see AX plus BY is going to create AY plus BX in this AB XY format here. I'll give some examples of that to kind of make it make a bit more sense. And so the example here, first, just I color code it here. We see the yellows are the AX, and the green is the BY, and it kind of breaks apart where now the A groups up with the Y, and the B groups up with the X and forms two new compounds here. And so here's an example here. I'm not sure where I pulled this from, but this is an example of a double displacement reaction. Silver nitrate, and sodium chloride. We've actually talked about this. I've mentioned this class a couple times in class. I think I've ask you to count how many atoms of oxygen there are in the silver nitrate portion. But you can see here, and these reactions are from ionic compounds. We have silver nitrate, which is an ionic compound, and then we have sodium chloride, which is an ionic compound. And what's going to happen is the silver is going to break apart from the nitrate, and the silver is going to become a positive ion, and the nitrate, NO3, is going to become a negative ion. And now our salt, table salt, sodium chloride, the sodium is going to break apart and form a positive ion. And then the chlorine is going to break apart and form a negative ion, as it always does. And these are aqueous solutions. They are in water. So you can see if the silver was positive and the chlorine is negative, that means the silver and the chlorine are going to team up. It's the way ionic compounds work. And then the nitrate, the NO3, is going to be negative, and the sodium, which is going to be positive. Those two are also going to team up, and there we can see it here with the chemical reaction here. Right here is this. We see our silver, tiny little silver dot, is now teamed up with the chlorine ion, and now that's silver chloride. And we have our sodium chloride is going to now, the sodium is going to break apart and team up with the nitrate. And so that's how this reaction kind of works. Just this two people break apart and kind of team up in a different way to form two different compounds. Well, let's talk about it a bit more. I've talked about silver nitrate all year, so let's just kind of let you see it, because this is one you can actually see. So silver nitrate, we talked actually desynthesis. A few slides back, we talked about desynthesis. When I take water and I desynthesize it into pure hydrogen and pure oxygen, and I talked about, hey, the hydrogen is actually explosive and it can go boom, which is why we call it the oxygen bomb. When we were on submarines, creating the oxygen air that we sometimes had to use. Well, silver nitrate is a process that we could use to test the water to make sure the water is pure. So what happens is we add silver nitrate to the water, and it has that double displacement reaction that we have right here. and the silver will bind to the chlorine, and the nitrate will bind to the sodium. And the benefit of this is, and this ties into chemical changes. Sometimes you can see chemical changes because when chemicals change, their properties to absorb or reflect light changes. So think about it. The property to absorb or reflect light changes. If you remember from physical science, if you've taken it, reflected light is what we see. If something is not reflecting any light at all, it's going to be black. We're not going to be able to see it. But by reflecting the light, we're seeing the light that's reflected. So when this silver combines with chlorine, the chemical compound changes. It is now going to be able to reflect light. So what we're going to be able to do, we're going to be able to see the salt in the water that's already been dissolved. All right, so here's why, again, why silver nitrate's kind of cool. Also, we see this silver nitrate kind of form up. It's going to fall down because it's heavy. It's going to be heavier than the water itself. It's going to kind of fall down, and we're going to see it form in the solution. And we call that in chemistry precipitate, like kind of precipitate, like precipitation raining down from the sky. And we'll discuss this a bit more in the solution chemistry in the second semester, unit 2, I believe. All right, let's talk about how it's going to work here. I'm going to show you 2 containers of water. They both have deionized water in them. I'm going to put some table salt into another one. Ideally, I'd use the same size containers, but I don't have the same size glass containers, so we have to do what we can do. The salt I'm using is not pure sodium chloride. It's actually iodized salt, the cheapest stuff I could get. I did verify that the iodine present in this test, it would react, but because there's so little iodine, I'm talking like, I think it's like 35 or maybe 100 micrograms per 1 gram. Tiny, tiny, tiny. It's so little, it's nothing you can even observe. So with most chemical equations, they don't even represent iodine being in the process, but it is there. So we're going to do this. And, you should hopefully have a good idea which one this is going to react with the sodium, with the most of the silver nitrate, the one with the ionized water or the one with the salt. So let me see if the document camera is working here. All right, looks like it's working. Okay, so here's our contestants here. I have deionized water here, and deionized water, folks, it's actually also made by a double displacement reaction. Often water will naturally have sodium chloride in it, especially if you make water from seawater. It's boiled. There's always some sodium and chlorine that kind of carries over. This ties back to how to separate mixtures. That's actually unit two stuff, or unit 1, unit 2 things. And in order to fully get that sodium and chlorine out, you have to go through a deionization process, which actually strips. It physically removes the sodium and chlorine from the water. And there's different ways of doing it. You can't buy this. You usually have to order it. It's not exactly the best stuff you don't carry in supermarkets because it's not good to drink. Your body actually likes having the ions. So I've been told before, if you drink it, it might make your stomach upset. So I don't recommend doing that. It won't kill you though. But right now, both of these containers have just a sample, just around 40-ish milliliters of deionized water. Here's my cheapy salt. And let's just use the big one here. I'm going to pour a little bit, not a lot, a little bit of table salt in here. And give it some swirl to about the salt absorbs. And even though we can't see it, the salt is already going into solution and breaking apart. So it feels hot. It'd work faster. We'll learn more about all this stuff in second semester. A lot in second semester. We'll probably see some salt particles at the bottom because it doesn't take a lot to break it up. I'd have to heat up the water to get it all gone, but yeah, that did most of it. You can see there's very, very little. I'm going to show the camera. You probably can't even see it, but there is like a tiny bit of salt right about right there. Yeah, you guys can't even see that, can you? Maybe. Yeah, I can't even see it in the camera. I can see it physically here. All right. Now my sodium chloride, and by the way, it's in a brown bottle. And other things you will see in chemistry and biology sciences that are in brown bottles like this are like this because they're light sensitive. They don't like light. In light, they change, they actually go into a chemical reaction and change. Silver nitrate is used for photographic film. Photographic film needs light to change it. That's just why. You may have hydrogen peroxide at your house. Hydrogen peroxide is in a brown bottle because hydrogen peroxide reacts with light. Not sure if you knew that. All right, so I'm just going to take, I'm going to take 3 drops in each bottle, each container here. And so we have one with salt. We have one without salt. Which one should show us something? I should probably take this up first. It's been a year since I used it. All right, so you probably said, well, Mr. Sherwin, you kind of told us the answer. The one without salt's not going to do anything. So I'll put just 2 drops. 2 drops in the one without salt. 1, 2, now it's 3. Okay, that's 3 drops. Get a bit closer. And, well, I can't see a difference. Comparing the two, I kind of swapped it on you. It's the one, but there's really no difference here. All right, now let's put 2 drops in the big one, which you saw me put salt in. I'll try to do 2 drops. 1, 2. And you're probably seeing already, you see some stuff floating to the ground, floating to the bottom. Look at that. It's already formed some chunky stuff already. Let me, sorry about the vertigo here. I'm going to kind of modify the camera as it falls down. I'm sorry about that. There we go. And a piece of white paper to help maybe see a little bit better. See the chunky stuff right there. If I swirl it around, the entire water is going to turn cloudy. See how it's kind of cloudy there at the bottom? It looks almost like smoke. Swirl around a bit. It is very cloudy. Very cloudy. Oh, my arms are over here. Compared to the regular water. So there you have it. The sodium chloride, which is broken up in water, it reacted with a double displacement reaction with the silver nitrate, where because the silver nitrate also broke up in water, the silver bonded with the chlorine ion, and the nitrate, being a negative ion, bonded with the sodium ion. And that would be your double displacement reaction demonstration. Final little tidbit about silver nitrate, because it's a chemical, might as well talk about it. Some neat things about here. It's good for good stuff. There's good stuff for this thing. It's actually used for in medical purposes. It can cauterize wounds. Used to be when I was your guys' age, I was a teenager. I had nosebleeds like 2 or 3 times a week. I went to the doctor. He's like, okay, we can fix this. And he took some silver nitrate and he put it up in my nostrils really high. And he cauterized some blood vessels that are very close to the surface of my nose. I have not had a nosebleed since I was a teenager, folks. It didn't feel good, but it worked. It's still used to cauterize modern medicine and modern surgeries. If you know anybody who gave birth via cesarean, they often use silver nitrate to cauterize that wound to make sure it doesn't pop open again, even though they do still put some type of stitches in there. I did mention it's used for photographic film, so there's other uses for it. Oh, it used to be used for mirrors. Yeah, a long time ago, it used to make mirrors. And if I had to think it's sulfuric acid, I could try that. But getting sulfuric acid is a little bit harder to do when you work out of a garage. All right. Hope you enjoyed this. That's all we have for this. This probably wraps up the reactions demo. In this thing you've watched, combustion reactions, where we have a chemical that combines with oxygen, releases heat and light. You've seen a synthesis reaction where you have 2 chemicals to combine with 1 or more to create a new chemical. We've talked about the decomposition reaction where 1 or more chemical breaks apart and forms new chemicals. We've talked about the single displacement and double displacement reactions, which you really deal with ions, often a lot of times ions in water, where the ions break apart and then they bond to a new ion, form a new ionic compound. Double just means, there's 2 in this case. And oxidation reduction reactions, remember that acronym OIL RIG. Oil is loss and reduction is gain. And magnesium. Pretty fun stuff, huh? All right. Have a good one.